All right. We are getting there. It is 3 p.m. in Paris. And we are going to get started with this webinar in a few seconds. So just for introductions, why the remaining participants are joining. I go to the first slide. Yeah, thank you. And that's good. You can go to this one, introduce myself. I will be hosting this webinar, and my name is Axel Fromont. I am in charge of developing digital solutions activities within Framatome with my colleagues in the different business units. And I am glad to welcome you to this webinar series on our digital solutions for nuclear and critical industries. What's interesting is this is a long haul process. That's why I had this quote here. We need to start now because introducing digital, let us face it, in our industry is often challenging. We operate in a complex environment and a highly regulated one. So I'm sure everyone on the call shares those particular constraints for introducing digital solutions in their environment. So let's move on to the first slide, and I will introduce you to what we will present today. So this is the second webinar of a series of digital solution webinars, again, for nuclear and critical industries. We focus today on presenting very concrete examples. We decided to present to you like experience feedbacks from things we've implemented in the field. And the topics today will be about plant performance, maintenance, and field operator safety. I'll come back to that. The webinar is going to be followed by a live Q&A at the end. Let's start with a few housekeeping items. Next slide, please. Yes, so a few points. First, this is a 60 minutes sessions, 45 minutes of presentations and 15 minutes of Q&A. For the Q&A, you will need to use the chat button, not the Q&A, that's the chat button on the bottom right of your screen, and then select all panelists so that everyone can see your questions and your remarks, and we will cover them during the presentation or at the end. Let me remind you as well that this webinar session is recorded so that we can share the content at a later date and give you access to a replay of the webinar. Okay, move on. So at Framatome, we like to start each meeting with a safety and security message. And that's quite important to us because safety is really part of our DNA. And I think if you come from critical or nuclear industries on this call, you will definitely share that with us. Safety covers much beyond nuclear safety. First, this is the safety of persons, your colleagues, your families, your loved ones, people around you. And that's why everyone's health is our concern at Framatome. And we care about that, and we encourage you to be vocal about it, to don't hesitate to speak when you see something dangerous, even if that is to your parents or to your teenagers, say it loud. So that's important. Take care of the persons around you. In the digital age, there is another insidious disease that is spreading, and that's the hacking of your personal and business data. So we want to encourage you to be vigilant about your cybersecurity, and that's also part of your safety and your security. So together with us, take care of the people around you and take care of your data. Those are two different important aspects of your safety and your security. Thank you. Let me get started with now the topics of today, which is about digital solutions for nuclear and critical industries. I guess that most of you in the audience know Framatome very well. We are a world leader in the design, manufacturing, and maintenance of nuclear reactor and SSS specifically, and associated fuel supplies or assemblies. In our core market, Our digital solutions are relevant throughout the life cycle of the nuclear power plants. As you can see at the bottom here, or the tops here, sorry, from new nuclear projects, new build, to plants in operations, to plant long-term operations when they need to be extended, the life is extended, and finally to dismantling and decommissioning after final shutdown. So digital spans across the whole life cycle. Those are very various solutions, and they cover very different aspects of the nuclear plant. Now, you see here that we also operate in other critical industries, such as defense, healthcare, and other industries. They have in common with us that they share a common focus on safety, on security, and on performance. And typically, they operate with very critical components and in highly regulated environment. And we'll find that again and again as a key characteristics of digital in nuclear. Move on. I think my next slide please, and I will introduce you to 5 dimensions in which Framatome is focusing its digital effort. And what's important here is like, we are not going after digital as a technology for itself. We are really looking at solving concrete and practical industrial issues. So we want to measure ourselves on our impact on safety and performance on those areas. And I'll go briefly over the 5 ones. First, safety and security. As I said, this comes first. For us, we cannot pretend we can maintain in a safe and secure fashion the different components which are running in a nuclear plant without covering cybersecurity. This is a critical and rising risk, an important element of the solutions we provide. And here we're talking about how to use solutions and services to identify the vulnerabilities, to protect critical assets, to detect an intrusion. And we provide a range of services that range from risk analysis, mitigation plans, system hardening, patch management, or compliance management. So that's a very important and critical aspect of our focus on digital. We're not going to cover that today. So let's move on to the second area, operations and control systems. This is really inherited from our long-standing expertise with digital INC systems. They are deployed today in many modernized nuclear plants. These are software and hardware solutions dedicated to real-time control of industrial systems, as well as predictive system for assisted operations. Number 3, third category is augmented engineering solutions. These are solutions which are meant to improve, so reduce the cost of engineering and improve its quality. And this is really for design engineering teams. On the previous webinar, we discussed 2 examples. One with Elvis, which was a solution for early simulation and detection of inconsistencies on the requirements, as well as Arcadia, which was a scientific code system for fuel assemblies. Fourth category is augmented operator solutions. These are solutions to allow safer operations of the field workers in nuclear plants. So typically operators in the field, either in the shop floor or in the nuclear plant. We will have an example today, which is about securing and ensuring the safety of those operators in the plant, while dosimetry is a key element of their job. Fourth and fifth category, is about asset management. These are a broad range of categories which are meant to secure and facilitate the monitoring, diagnostic, and maintenance management of critical assets. And we will have 2 examples today, which I will go into further detail later on, to facilitate the diagnostic and problem resolution on critical components in the nuclear plant. Yeah, we move on. Very briefly, next slide. I will go over what makes us different in digital. And it's not just what makes Framatome different, it's what makes us, everyone on this call who is interested in digital, different. And I want to open then at the end of the call a possibility for discussion and reflection on this, that we are not making digital like a startup or like a Google would do. We have in mind very different elements. Criticality, we deal about critical system that cannot fail. Complexity, there's no more complex system than a nuclear power plant, or very few. Sovereignty and independence, you need to maintain a tight control on your supply chain. You cannot depend on third-party software that you do not control. Traceability, number 4. That's where those are where you have the consequences of operating in a very regulated environment. You need to prove that what the value you're bringing is actually dependable. And finally, long term. You need to be here for the long term. Next slide, please. I will introduce now the 3 speakers who are going to take you through 3 very specific innovations, improving nuclear power plants' performance, maintenance, and operator safety. First, we will hear from Loïc Pinel, who is a 3D software specialist in our teams in the install-based BU. And he will take you right in the field where workers are operating in the plant, in the nuclear plant, and they need solutions to contribute to their safety and optimize their dosimetry exposure. Then we will hear from Clara Boisserand from Microscope, and Clara will present how the Microscope solution has helped EDF and others increase thermal performance. That's a conversion between thermal energy and electricity by using a digital twin asset-based, digital twin-based asset diagnostic system. And finally, Marie-Pierre Courouble is a product manager for INC monitoring and diagnostic solutions, Pulse, and she will present how Pulse helps detect and anticipate failures in critical INC components, instrumentation and control components. I will hand over now to Loïc, and we'll start with how to make the solution that help to make the worker in the field safer. Loïc, your turn.
Thank you, Axel. Hello, everyone. I'm Loïc, and I'm really glad to welcome you today to present you how the digital and the mixed reality can help us to create added value during the maintenance in the nuclear industry. Today, I will give you an overview of our solution H2V. Next slide. As you know, Framatome perform maintenance inside nuclear power plant. We are used to work under radioactive atmosphere. So the challenge for us is how to keep operator informed and away from harm. Today, there is several problems. The first one, dosimetry mapping is inefficient. Today, we request a team comes, take measurement, radiometric measurement, then they analyze it and then deliver you the result. It takes a bit of time and no standard methodology. And what about when the condition change on site? Here we go again, call, team come, measure, interpret, and then give you the result. Second point is the lack of visibility for dosimetry and radiation. 2 aspects in that. First one, of course, for the operator itself, how it can be aware of a hazard that you cannot see directly with your own eyes anytime, not looking at your dosimeter, but anytime. Second point, if you think in terms of resources and the dosimetry capital that all the team have, you need to have an overall view, life in real time, to optimize your resources, because it becomes a cost. It's linked to cost. Third point, it's difficulty to set an efficient remote technical assistance. Sometimes when you perform a task, you need an expert, you need someone to help. And for different reasons, he's not here. Maybe he's away from the site or cannot come for some reason. Non-quality maintenance. This is a problem, and a very known cause is because the operator had a difficult access to the working documentation while performing the task. And the last point, which is a very important one, is lack of dosimetry simulation during trainings. We all know that training is the key to succeed maintenance operation, especially when you are under high constraint environment, like we are in the nuclear industry. So we need to take this into account to anticipate waiting zone, gesture, path, where to go, and coordinate everyone around that. Next slide. So here we come with our solution H2V suite. This is an augmented nuclear field worker application. This solution is based on mixed reality solution using HoloLens 2 device. What is HoloLens? HoloLens, it's this. It's kind of glasses that you wear. You look very cool when you wear that, but the main point is you can see reality through the glasses, like normal glasses. And the technology allowed you to overlay information on top of what you're seeing through the glasses. With that, we can 3D capture the real environment, working environment, real or simulated radiological atmosphere. Those 2 points are actually, we are drastically improving the input data to work. This is a key. Then with this high quality data, we generate high density dosimetry map, more detail than the standard way to do that. Visibility of identified risk. We can bring to the team and attract attention on risk using those tags that we can put in the scene. And the supervisor can identify additional risk and push it into the scene so everybody can share the same environment and be aware of. Last point is a real-time access to documents and technical assistance. We are able to send remotely the right documentation to the worker, for him to perform his task if he needed. And we can open a video link and audio link with him using those cameras right here. So literally, we can see through his eyes. Next slide. So here we are, we have the operator view. So on the right picture, you can see there is 2 documents got displayed for the operator to help him performing the task. There is 2 small white tags. Actually, this is the hologram that show the hazard. Here it's a radiometric 1 hotspot. And at the bottom of the picture, you can see a grid, a colored grid. So this is our dosimetry map. And it's color coded from green to red. So it's very natural and very easy to understand and to be aware of your surrounding. If you look at the partner, and this is the picture to the right, you can see floating above his head is dosimetry information. Of course, you can see also your own dosimetry information without looking at your dosimeter. This is important to take care to help taking care of each other and to be this awareness inside the team. Next slide. How does it work? Very easy. This is not an heavy system. Actually, every operator are wearing a dosimeter, like usually, actually. The team have one radiometer to measure radiation, like we used to have. Every operator is wearing a pair of glasses, Google. There is a supervisor behind a computer sitting down around close to the site. And everything is linked with a close Wi-Fi connection. With that, the first worker go to the sites and he walk all around with the radiometer and his HoloLens. This will create the 3D capture of the environment. And in the same time, we will acquire dosimetry points using the radiometer. It's automatic. If you are not under real radioactive environment, you can always simulate dosimetry points. This is mainly for trainings, right? When you collect all those data, high quality data, then you click on generated the dosimetry map. And after, let's say, 1 minute, you get it. And then you're ready to work. Next slide. Benefits. Yes, to summarize, we surely increase safety in operations. We get an efficient dosimetry mapping. We can perform really efficient remote assistance to reduce the non-quality maintenance. We have a better management of dosimetry during the ongoing operation. And we really improve the pre-job briefing and the training to the real environment of intervention. That's all for me. Thank you for your attention.
And many thanks, Loic. I want a suit like that on the picture for my next presentation. All right. I hope you enjoyed being in the plant together with Loic. Now we're going to move on to the next topic, which is about how digital twin-based model can help us anticipate and perform diagnostics on maintenance. And this is going to be led by Clara Boisseran from Microscope.
Thank you, Axel, for the introduction. So hello, everyone. I'm Clara Boisseran. I'm the Chief Business Officer of Microscope. And today I will present you our software, which is dedicated to monitoring and diagnostics of power plants. Microscope is actually a startup created in 2018 by EDF, which is the French utility. And we have a strong partnership with Framatome today in this nuclear market, providing a complementary and common offer on the market. Next slide. So first, we start with an actual challenge faced by one of our customers in the nuclear power generation industry. In this case, in this nuclear power plant experiences losses up to 2 megawatts for 18 months since 2017, without being able to understand the root cause nor precisely calculate the loss. Microscope software was deployed in July 2018, and it pointed out a bulb leakage of an average 20 kilograms per second that was not identified by the site at the moment of the deployment. It was actually coming from an air-operated valve controlling a ventilation line. So 3 months later, the detection drastically and rapidly increased from 2 megawatt impact to 7 megawatt impact. So the severity of the failure then worsened by 3 times, passing from 20 kilograms per second to more than 60 kilograms per second. So at this point, the leakage was too important and the site needed to launch a maintenance action. So by running the Microscope after the maintenance action, the site was able to evaluate the effectiveness of its own maintenance. And the Microscope actually precisely quantify a reduction in losses due to the maintenance, but the plant was still losing 2.5 megawatts. So based on this evaluation, a second intervention was required by the site to close the valve properly. So this time the maintenance action was totally successful. So at the end, Microscope successfully identified and qualified the fault corresponding to the megawatt losses. It also tracked maintenance operation results to check consistency. And last, it enabled quick maintenance in 2 weeks' time and capitalization on the rest of the fleet. In total, if Microscope was deployed earlier, the power plant could have saved 18 months of unknown losses, so with an average of 2 megawatts. So it's actually a total of losses of 15,000 megawatt hours. It means at the end a saving of 1.7 million euros, which is quite considerable. Next slide, please. So the use case, the case study that I was just mentioning before, it's actually a common challenge faced by the nuclear power plant industry. It's basically thermal performance and megawatt losses. But there are actually other challenges. Challenges based on condition-based maintenance in order to reduce the cost of the maintenance operation and obviously extend or enhance the lifespan of equipment. Performance is very key as well to find the lost megawatts on the plant and locate the origin of those lost megawatts and maximize the availability of the plant. Simplicity is key. With the multiplication of the tools on site, it requires less time spent on the tool, including Excel tool, an easy interpretation of the results, and one common platform in order to ease the interpretation and the analysis on the circuit. Last is asset knowledge. Power plant needs to anticipate the behavior of aging materials and need to centralize data of the assets. So ultimately, all of these challenges lead to impact on thermal performance. Next slide, please. So what is exactly our solution based on all those challenges? So we provide a software for monitoring and diagnostics. This software aims to understand the faults on the equipment and quantify the energy loss or the megawatt loss on industrial equipment. To do so, we use digital twin technology. It's actually a hybrid digital twin using physics-based approach, thermodynamic process, and also an operational experience with historical data. Today, we have 300 users, over 68 power plants, and 5 countries. We have in-house experts at modeling complex industrial processes using knowledge-based libraries and state-of-the-art libraries. Only in 2021, equipping the 56 units in the French fleet, we identified 40 megawatt hours per unit of annual total loss. The diagnosis that we are giving in the software is actually a relevant and critical input used to improve planning on purpose maintenance operation. Next slide. So how does it work? We actually have mainly 2 key technologies. So our physics-based digital twin is used as a nominal reference to detect symptoms or to detect deviation for each point of measurement, each physical measurement on the process. As a reference, a digital twin of a 400 megawatt counts around 150 sensors and 10,000 physical equations. So the difference between what happens from the sensors and the reference value from the digital twin is actually what we call a symptom of an ongoing fault. Actually, one fault can be responsible for multiple symptoms, and each symptom could be caused by multiple faults. So that we, in the digital twin, use as well a failure library that is simulating the failure or the fault and compute their impacts over all parameters. In a few seconds of calculation, Microscope used an inferential engine, which is studying every possible scenario within the failure library to find, through a probabilistic approach, the best combination of faults to explain existing symptoms. This is the last phase, the diagnostics phase. Next slide, please. So, as you can see, we have our digital twin, and we used in this digital twin and enrich the digital twin with fault mode, which will help us to characterize for each fault the different relevant symptoms. As you can see, we embed around 70 possible faults in the model. And this model is actually, again, leveraging both experiences, physics-based knowledge and operating experience using historical data. Next slide, please. And as you can see here, the key features today that we are deploying on the software as a SaaS model, it's basically 3 key features. So first, we explore and demonstrate over the period the key parameters that are evolving over the time. These parameters are actually accessible over the plant history and calculated according to thermodynamic properties, law of physics, and mathematics. So first, we explore the measurement from the senses over the time. Second, we detect the symptoms, which is again the difference between the digital twin and the measurement. And this is automatic and real time. But last is we understand the diagnosis by giving the related fault that can explain those symptoms. And we are going to as well quantify the impact of those faults on the power plant. That's it for me. I will be glad to hear any questions at the end of this session. Thank you very much.
Thank you, Clara. And after saving dosimetry, now we're saving megawatts. Start raising your question if you want. Reminder, you can use the chat at the bottom right and share your chat with all the panelists or all the invitees. I will hand over now to Marie-Pierre Corouble, and who is the product manager and solution manager for the Pulse solution for monitoring and diagnostic in critical INC systems.
Thank you, Axel. So my name is Marie-Pierre Corouble. I'm solution manager for INC, for services. And today I'm going to introduce a use case that we encountered a few years ago related to the road control system with a utility operating a PWR plant. Next slide, please. So the utility met a loss of position of one road, and they were not able to identify what was the root cause of the problem. Several possibilities were contemplated by the operator. It could be due to a module failure. It could be due to RPN line failure because of poor contact, of loose tightening. It could be also due to a sensor failure because of coil degradation, for example, and it could be any other reason that was not identified at all. So the utility turned to Framatome to ask for support, and we suggested to perform a pulse cables and connection expertise, enabling to have a more precise assessment of the situation. Next slide, please. So you can see here on this slide the diagram with the setting up for the road control system pulse cable and connection expertise that we provided. And it is exactly how we plugged the system. So the care tool that was used for this pulse expertise was plugged on the RCS cabinet at the rear of the cabinet, enabling a deep analysis of the whole faulty line from cabinet to the RPI sensor, thanks to a series of automated tests. We conducted some resistance measurement and insulation measurement on the faulty line, but also on healthy lines to get some reference signatures. Some reflectometry of the RPN lines were also conducted to also have a reference signature. And some reflectometry of the two lines showing failures for which we were looking for were also conducted to search for non-friend contacts on the different connections. And an analysis of the reflectometry curves was done to compare at the end the healthy and faulty line curves to detect any insulation degradation, some cable cross sections, some connection defaults, any other failures that could happen. And the pulse cables and connection solution enabled to establish a quick identification of the failure root cause, which was due to a problem located at the electrical penetration level. Once this diagnostic was established, some additional tests were conducted to perform this root cause. Cables were moved at penetration electrical feed-through level, both on both sides of the penetration levels at electrical building and reactor building sites. And these tests confirmed the diagnostic that had been established by the pulse expertise. Next slide, please. So if we summarize this use case, the pulse cable and connection expertise performed on these RCS lines made it possible to carry out a complete assessment of the suspected faulty line up to the RPI sensor, and this within a few minutes. And it confirmed the atypical behavior of the faulty line, and it enabled to identify a non-open contact failure at the electrical penetration level on the electrical building side at the level of the red terminal lug. This is very precise. And it demonstrated that the RPI sensor was not the root cause of the failure. Because what is really interesting with this pulse cables and connection expertise is that in addition to locating very precisely the defaults on the lines, the expertise also enables to demonstrate that all the other elements of the lines which are expertise are healthy and fully operational if no default is detected by the expertise. And it is particularly interesting if you suspect that your RPI sensors may be aging and could be the root cause of the problem, even if you don't really know if it's the case. And in that case, without having a specific problem, even if you have no problems on your lines, conducting a pulse cable and connection expertise can bring you RPI sensors, aging and health status on all your RPI sensors. Next slide, please. Now, if we have a look on the pulse solution that was implemented in the scope of this use case, overall look, Pulse is a comprehensive range of services to monitor the health and nuclear safety of INC critical equipment, allowing to detect and anticipate potential failures and issues before they occur. It is a predictive maintenance solution that helps utilities to reduce risk and costs for their INC systems. All Pulse solutions are based on a simple, efficient, and identical model for all the equipment monitored through Pulse. Some specific and dedicated maintenance tools to collect data during maintenance activities. Data collected are analyzed by Framatome experts who will perform some specific and dedicated recommendations. And data collected are stored and compared along the years. And the combination of automated tests based on specific algorithm and the expertise of Framatome specialists make the Pulse solution a proven solution of predictive maintenance for INC equipment. So this is all today, and if you have any further questions, I will be happy to address them during the question and answer sessions. Thank you.
Excellent. Thank you, Marie-Pierre. This is the end of our first part of the seminar on the presentation from Loïc, Clara, and Marie-Pierre. I encourage you three to put your video back on as we are going to take the Q&As from the audience. And we'll start taking them from the chat where a few questions have already been raised. So let me take them in order. I think the first one was for Loïc. Sorry, no, the first one was for Clara from Microscope. How many nuclear plants outside of EDF are currently using Microscope services? Could you share information about their experience and performance?
Yes, sure. So first of all, we equipped the full French nuclear fleet, which is 56 nuclear power plants in France. But we actually also expanded to the UK fleet, so typically Sizewell as well in the UK. We also, I can also give you the reference of Electrabel in Belgium, where we also equipped Microscope, and they now used Microscope software for 2 years on Tihange plant. On top of this, I can tell you that we are working with 3 other customers in the nuclear market, especially in the US. So far, I cannot mention yet the name of those customers because we are just finalizing and switching to subscription. On top of this, for your information, we are also providing the software for combined cycle gas power plant as well, where we have many different customers in Europe and in the US. Regarding the performance of the software, I can say as well that, as you could see in my PowerPoint and my slides, that only in 2021, we detected 40 megawatt hours of energy losses per unit, which is quite relevant and quite critical. And it actually refers to more than 300 faults. And the software itself is actually showing a reliability rate of 87%. What does it mean? It means each time there is a diagnosis given in the software, the user can confirm, and actually 97% of the time, the diagnosis result is confirmed and validated by the user. So it's also a proof for us that the diagnosis is true and validated by the power plant itself.
Excellent, impressive. I have another one, I'll group them because it's more consistent. Another one on Microscope, which is about whether a Microscope solution is applicable to all reactor types.
So today we have experiences in PWR and BWR. This is our let's say the 2 type of reactors we have experience on. But yes, we have the expertise and modeling experts in-house that can actually adapt and create and implement a digital twin for new reactors. You just have to consider that it will just take longer time, maybe 2 additional months for us, or maybe more, in order to adapt and embed the expertise. But yes.
Excellent. And how long, I think you are kind of starting to respond to this, but this is, how long does it typically take to set up the model for a digital twin?
So today, considering that we do have experiences on PWR and BWR, you can consider that the digital twin phase is actually 6 months project, 6 months implementation. And as I was just saying, if it's a new type of reactors, then we should extend for several months, depending on the complexity of the plant.
Excellent. I'll switch the question to Loïc. Let me go back to the beginning here. What is the material for capture dosimetry data?
Yes. So what's brilliant is it's nothing particular, actually. We are using the same radiometer than already here on EDF nuclear power plant, the same device. We just perform a tiny operation inside. We had a specific module to allow him to communicate data. And here it's directly on view in our system. And this is the same also for the dosimeter that all the operator carry. It is the same, a tiny upgrade, and that's all, ready to go.
Excellent. Facilitate adoption by the user without asking for new things, except for the cool glasses, of course. Okay. Next question. If we want to use data from previous session or data external to H2V suite, is it possible?
Yes, it's totally possible. And what's make it great, you can reuse your data. You can take the best value of your data when you are working to have a very detailed environment and mapping, as we see. And of course, when you have this quality data, you want to reuse it. You want to be able to train with it or to get prepared for the next operation. And you can totally bring this data inside the engine back or external data.
Excellent. Thank you, Loïc. I have a question from Marie-Pierre. So how did the operator do to identify the root cause on a faulty line before using Pulse? So how much time did they gain using this solution?
That's a good question. In fact, without the Pulse automated test, in fact, the operator has to search until he finds the root cause. So he starts by replacing some modules, which he finds maybe the root cause. And then if after some test, after replacing the module, nothing changes, then he will switch to test the cables themselves to be if there might be some degradation in the cables, etc., etc. So it could take days, according to examples, before finding the real root cause. Whereas with the Pulse solution, as you are connected on the full line and with automated test, you are able within 7 minutes to get the result for all the lines. So of course, if you had the chance to find the root cause, if it was, for example, before the Pulse expertise, just a module failure, you change your module, okay, it's fine, you managed to find the root cause. But imagine if it's not that. And in the use case that I explained today, before being able to identify that the problem was on the penetration, it had taken many, many days, and the operator could not find where was the cause.
Okay, excellent. Thank you, Marie-Pierre. Another question to Clara from Madame. When you apply your system to a unit, you install new sensors also, or gather data from existing measurements and systems?
Yes, so the response is no. We try as much as we can to use the existing sensors of the plant Actually, it's a good question, because during the digital twin phase, we actually start by reviewing the instrumentation, by mapping the instrumentation over the plant, and detect if the coverage of this instrumentation is right, is efficient enough to build a digital twin. So after this instrumentation mapping overview, we will be able to tell to the customer if they need or not to install new sensors. But so far today, we did not need to add any sensors. The most critical for us is not the coverage of the instrumentation, it's mainly the history of the data, meaning for each sensors to have a minimum of 6 months of historical data in order to build a digital twin. This is the most critical for us.
Okay, thank you, Clara. I think I covered all the questions in the chat. If anyone else want to add any additional point, don't hesitate. Let me check. I had a question for Loic. Yes. Is it fast to deploy the H2V solution to set it up? Or does it require any particular step? How long would you say?
It takes the time to wear the device, to switch it on, to go in the right application. Then there is another computer to switch on and a Wi-Fi router to plug. This is all for the hardware part, and for the operational part, one of the operator need to go first on the work site and walk around to capture the data. So of course, if the room is small, it takes maybe 2 minutes, and if it's much bigger, let's say 3 or 4. And then there is the phase to compute the dosimetry map, and this is really fast. It's less than 1 or 2 minutes. So,
excellent. So it's close to immediate. Yeah.
Yeah.
Great. Okay. Thanks, Loic. And thanks, Lara, and thank you, Marie-Pierre. I think we covered, sorry, another question from Alejandro about Microscope. Is it a pure physical model or is it hybrid neural network? Are there future plans in this direction?
Yes, so our digital twin is actually what we call a hybrid digital twin, because it's both physical model using around 10 to 15,000 of physical equation, so using the thermodynamic process in expectation, plus we also add a calibration on historical data. What we do is first we model the plant with the physical equation, and on top, for each components, for each measurement, we will look at the historical data, look at the best and optimal behavior in the past, and this will allow us to calibrate the expected value with the optimum behavior of the plant. This in order to be really close to the reality. So this hybrid approach actually allows us to have a relevant and very efficient way of detecting the symptoms, because we can detect symptoms that never occur in the past. This is, let's say, the added value of this hybrid approach compared to just a machine learning digital twin model. So the answer is both. Machine learning plus physical model.
Right. Thank you, Clara. I think this is wrapping up the seminar for today, and I really want to thank all the speakers and all the people who attended and raised very good questions. We have a couple of other sessions planned in this webinar series. One will be on December 6th, actually more connected to robotics, and we'll present our Robotics Excellence Center. And one on January 26th, where we will focus on innovative digital solutions and robotic solutions for dismantling and decommissioning. So just as a heads up on next webinars, which are currently planned. Very good. Don't hesitate to reach out to anybody who spoke today, and they will be glad to entertain follow-up discussions with you. You have the contacts here, and I think you can have access to this. Don't forget to revisit our solution portfolio, or everything that was presented when they are based on a particular product or solution is presented there on our website. I think that concludes our, I'm pretty sure this is the last one. Yeah, that concludes our webinar. Thank you everyone for their time and interest in this. I want to thank everyone for their time in this digital topic, and I'm really looking forward to exchanging with peers in the industry. I'm forward to exchanging with this digital topic, and I'm really looking forward to exchanging with peers in the industry because it's not something we will solve by ourselves. This is a long haul transformation journey. Thank you to everyone.
Thank you to our presenters and to attendees. Thank you so much. Bye-bye.
Thank you very much.
Thank you.
Bye.
Bye-bye.